Our planet is characterized by an atmosphere that consists mostly of nitrogen and oxygen. In addition, other gases are present in small quantities, such as noble gases, argon, helium, neon and krypton, hydrogen and greenhouse gases. These include water vapor, CO2, methane, nitrogen oxides, ozone and chlorofluorocarbons. CO2 makes up approximately 77% of all anthropogenic emissions, in contrast to only 14% of methane or 1% of CFCs. Greenhouse gases, especially CO2, have a significant thermal influence on the Earth's surface, which is known as the greenhouse effect. CO2 can remain in the atmosphere for up to 200 years before it is assimilated by natural mechanisms. The greenhouse effect is a natural process which makes life possible on our planet, but only if these gases are maintained at given concentrations in the atmosphere. A sudden decrease in CO2 within the Earth's atmosphere would turn the Earth into an ice ball, while a drastic positive leap would provoke a decrease in the heat emission of the atmosphere, thus increasing the temperature of the planet. There are several mechanisms called natural sinks that compensate for CO2 emissions in a natural way, such as oceans and forests. Greenhouse events, interglacials, and ice ages, glacials, have occurred throughout our planet's history. These events are in accordance with the natural oscillations of CO2 levels within the Earth's atmosphere. However, from 1850 till today, the world population has multiplied by 4, while energy consumption has multiplied by 80. Today's atmospheric CO2 content is by far the highest that it has ever been in the last 400,000 years. Earth's natural processes can no longer keep up with this excessive emissions, because the rate of increase of CO2 concentration is 10 times faster than before. Over the past years, scientists have proved that the rise in concentration of greenhouse gases in the Earth's atmosphere, and especially in that of CO2 of anthropogenic origin, is intensifying the greenhouse effect exerted by the atmosphere on the Earth's surface. Thus, this phenomenon is responsible for the global warming that has been observed in the last decades, the most spectacular result of which is the melting of the polar ice caps. Today, world annual CO2 emissions are at around 36,000 million tons per year. Spain is responsible for 450 million tons per year, while China and the United States are the largest emitters with 6,700 and 6,500 million tons per year, respectively. The EU countries of the European Union together emit 4,500 million tons per year. In the face of this alarming situation, a group of industrialized countries have committed themselves, through international agreements like the Kyoto Protocol, to reduce their emission of greenhouse gases, and especially of CO2. Some of the measures adopted by the European Union include a commitment to reduce its greenhouse emissions by 20%, to increase the proportion of renewable energy produced by 20% compared to 1990 levels, to increase energy efficiency by 20%, and to increase the percentage of biofuels in petrol and diesel to a minimum of 10%. All this by the year 2020. Today, the only way to keep up with the energy demands of both industrialized and developing countries, while at the same time fulfilling the objectives of the Kyoto Protocol in the short and long term, is to use clean energy production. 81% of the world's energy comes from the combustion of fossil fuels such as coal, oil and natural gas. The use of new sustainable energy technologies, combined with nuclear energy, only accounts for 19% of the total energy demand. According to estimations, this number may reach 35% by 2050, but the remainder will still rely on fossil fuel combustion. Therefore, a large number of international organizations, including the United Nations and the European Union, are promoting carbon capture and storage as one of the most immediate solutions for the mitigation of climate change. The technology involved in carbon capture and storage consists of capturing CO2 at the point at which it is emitted by industrial facilities and power plants, transporting it to a storage site by means of pipelines, similar to those used for natural gas transportation, or by shipping using road tankers. At the storage site it is compressed, and using a special injection well, it is injected to more than 800 meters deep underground. At this depth, the CO2 acts as a liquid, increasing its density and decreasing its volume. If we wanted to store all the CO2 produced globally in 1 year, on the Earth's surface it would fill a deposit of 350 kilometers in diameter by 200 meters high. Spain's CO2 emissions over the course of 1 year would occupy a deposit of the same height with a surface area larger than the city of Madrid. However, when stored at depths, the CO2 can be compressed to a volume 500 times smaller than on the surface, which makes geological storage the most effective. The mission of carbon capture and storage is therefore to close the circle, which starts with the formation of coal underground, continues with its extraction and combustion for energy production in power plants, and finishes with its capture, transport, injection and storage, once again underground. The key question is where to locate the geological CO2 storages so that they will be safe and secure. And the answer is already provided by nature.
La roca almacén debe ser una roca altamente porosa, con mucha permeabilidad, que además contenga agua salada y se encuentre a profundidades, digamos, mayores de 800 metros al menos, para permitir que el CO2 permanezca como un fluido. Este tipo de roca podría ser similar al que vemos en este afloramiento, donde tenemos una roca con una alta porosidad y permeabilidad.
In the pore space of the reservoir rock, the compressed CO2 can be injected in such a way that it acts like a liquid, which travels inside the rock. Above the reservoir formation is situated the seal rock, which would be very similar to this one, an impermeable rock which has sufficient thickness to impede the migration of CO2 to the surface. Therefore, the ideal geological storage structure consists of a porous reservoir rock in which the fluid can remain and which is capped by an impermeable seal rock to impede the migration of the fluid towards the surface. If we pour water on the surface of a porous rock, it is absorbed and stored within the rock's pores like a sponge. Conversely, an impermeable rock does not let the water pass through it, and the water remains on the surface. This new industrial use of underground space mirrors a natural process. Underground reservoirs of natural gas, oil, water, or even CO2 are in themselves geological storages, where these fluids have accumulated for millions of years until man perforated the seal rock to allow them to escape to the surface. The final goal, therefore, is to locate geological structures similar to these. In Spain, the target are deep saline formations.